Good morning, good afternoon, good evening, everybody. Welcome to this LinkedIn Live event from Welded Technologies. It's an honor to host you for the next hour on this new disruptive technology called RotoArray comPAct. Let me allow myself to introduce myself. My name is Vincent van der Wallen. I'll be your host for today, together with the team of Dan Groninger, who's our senior service engineer, and Ben Hoemske, who's our lead engineer. We will be showcasing you the technology of RotoArray comPAct. The agenda for today is we will be going for the next hour in 10 minutes into a presentation where we will be showing basically the technology on paper. After that, we will go live into demos. We have 6 parts that we will be showcasing in the live sessions, going from composites to fuselage to corrosion to welds. After that, you will have the possibility to ask questions. We'll have about 10 to 20 minutes. In the meantime, if there are any questions, please place them in the comment box, which should be on the right hand side of your screen. We will be looking at those during the presentations as well, and answering them. And otherwise, we will be answering them at the end. This session will be recorded, so if you have any issues with that, you are welcome to leave. But I hope everybody will stay on. Within Waygate, we were thinking about how to address the phased array market in a different way. Nowadays, there's a big need for doing phased array inspections, and the setup currently is by using probes that are connected to an instrument. We wanted to change that, and therefore our engineering department started developing the possibilities to make those changes. This disruptive technology that we managed to engineer is called the comPAct technology. Basically, what our engineering did is we reduced the phased array electronics by a size of a factor of 100. Basically, using the big electronic board that we used to have in the past by a factor of 100, miniaturizing to basically the size of your thumbnail. Also, not only the size needed to be smaller, but also the power consumption, because we cannot have the same power consumption if you miniaturize the board. Also, that was a big challenge, but they also managed to get that by a factor reduced of a factor of 20. Basically, miniaturizing the phased array technology, and the first integration that we are currently having is in the RotoArray comPAct. What is the value proposition of the comPAct? What does it enable us to do? Well, if we look at on the right side of the screen, we have a couple of items that really make a big difference. If the current electronics are embedded into the RotoArray on top of the tire, as you can see. Also, the weight reduction is one of the biggest items that which make it more portable to take along, whether you take it in flight or to any customer. It's weight reduction that we currently see in opposite of the existing RotoArrays is getting it from 4 kilograms to 2 kilograms. So that's a weight reduction of 50%. The biggest weight reduction is not really the system itself, but it's also that you don't need a system anymore like a big phased array device. So the only thing that you need to take along is the RotoArray comPAct itself, as well as a tablet, laptop, or any PC. Also, the costs are significantly reduced because you don't need a big instrument anymore. The possibilities are there to just to hook up the RotoArray comPAct towards a tablet, and then you're set to go. The reason why we also have the lighter weight is that we don't use the coaxial cable anymore. We switched over the coaxial cable because the phased array electronics are now embedded on top of the probe. We can use the USB cable towards the tablet or laptop, and therefore there's no need anymore for the coaxial cable. This also enhances the signal to noise ratio because there's less possibility of getting noise on the cable itself. Using a Windows tablet enables us the flexibility and connectivity. We have embedded, or we have taken on board tablets that you can purchase at Waygate Technology, but any tablet that you have yourself or company-owned tablets can be used as well. We know that there's also sometimes problems with having cameras on board, so you can also purchase tablets that don't have these cameras or have embedded software on board from the systems itself. Planning, acquisition, and storage and analysis can be done on the tablet or laptop. Basically, also utilizing the company-owned software for doing planning, making this system a versatile system that can be used across the board. If we switch over to how the design improvements look like, we can basically see that the electronics are currently fully embedded onto the probe set. We have an improved handle on the top side. This allows for better grip and more suitable for gloves. Also, the two buttons on the top that we can see here have three functionalities: start, stop, as well as index. Also, the buttons have LED indicators with different colors. It means that you can basically see on the device itself whether it's good to go, whether you have to initialize the setup, and you can actually see the complete status on the device itself or on the buttons itself, so you don't always have to look at the system. The integrated encoder makes encoded possibilities. Also, the RotoArray comPAct has less use of water, so you just need a little bit of spray on to get it going already, to make sure that your coupling is there. But most and utmost, if we look at the connection cable, the integrated electronics makes for enhanced UT performance. To explain you a little bit more about this enhanced UT performance, I'll switch it over to Ben, and he will explain a little bit more on the performance of the system.
Thank you, Vincent. As Vincent stated, we have a fully integrated system, and what this allows us is to have a really short analog signal path. We don't catch the noise on the cable because the analog path is just 50 millimeters long. We just have very less power consumption, which can go down to 10 volts and saves a lot of energy. So your tablet is even running longer with a longer battery life. Due to this short cable length, we also have a better resolution, and you see down there on the screenshots the noise reduction comparing to a traditional phased array ultrasound instrument on the left-hand side and the comPAct technology on the right-hand side. Vincent, next slide, please. We have different views on our software. Our software is an app-based software, and this, what you see here, is the final inspection screen. There you will have an A-scan on the top to evaluate each and every shot you want to look at, and down there some overviews of the amplitude and time of flight. Then we'll later on go in a practical session more into detail to that. So yeah, we can go to the next slide. Having such a fully integrated system, it also comes to the certification. The system is fully tested against the standard 18563, the phased array standard. And with part one, we first test just the electronics, which are completely integrated into the axle. We test the probes against the part two standard, so we make sure every element is alive and is in a certain range. And when the system is fully assembled, we do this part three test, which is normally user standard, but it is for combined systems. So we check if the whole system itself works as we designed it. Now go to the next slide. To wrap it up a little bit, this first instrument we just designed here is a phase rate probe with 64 elements and at a frequency of 5 megahertz. I want to highlight the pulsar voltage here because, like I said, we can go down to 10 volts and still have some good results on thinner composite materials, but we can also go up to 70 volts. The maximum power consumption is due to the USB 2.0 standard specified by 2.5 watt. Typically in a normal range, we use just 1.5 watt. So you can roughly calculate how much time you have with your battery life. On the right-hand side, you can see our minimum system requirements, which basically are aligned to this to the Microsoft Surface Go tablet, which is kind of a iPad-sized tablet and is easy to handle. Nevertheless, we also, like Vincent says, have in our offer a ruggedized tablet from Dell, which might be more suitable for the industry environment. But in the end, it's your choice. The only demand we have there is it is a Windows tablet. Is it Windows 11 or Windows 10? Doesn't matter. Okay, that's it from my side, and I pass it back to Vincent.
Thank you, Ben. Yeah, as mentioned before, we wanted to keep the presentation to a minimum. I think it's more important to show the actual applications. We will be switching over from the US to Europe, where we have our specialist Dan that will start with a Plexiglass demo plate. That demo plate will also be in combination with the detailed explanation of the screen. Then after that, we will switch over to Ben with TCG on composite step block, and so on and so on. So for now, Dan, the floor is yours.
Oh, all right, thank you, Vincent. So I'm already set up here with my RotoArray and the plexiglass block with a number of indications milled in from the back. We don't need a lot of couplant, just a spritz of water. Let's make sure the water is nicely distributed. Okay. Now, a couple of things. Let me clear the screen quickly. All right, a couple of quick pointers. The top two views are live. So we have our A scan and we have our E scan or sector scan. So the A scan is, of course, one individual shot through the part straight down from the top. Okay. The E scan is one slice across the part directly under the probe. So we have a 64 element probe. We're firing 4 elements in a group, stepping by one. So we do 60 steps across the part, looking down through. And each of those 60 steps is shown on the sector view, the E scan, if you will. And the live A scan is the A scan that is directly under the beam cursor that I can select to move back and forth. So those are live when I'm not actually recording and when I do not have data already recorded. So let's go ahead and record a scan. The wheel is encoded, so our movement is encoded. We do have a laser pointer to help in alignment. And we have start and stop buttons right on the handle. So once you get everything set up and you're ready to do your scan, you don't have to reach back to an instrument or reach back to your computer to start and stop the scan. The buttons are right here on the handle. So I'll press the start record button, run down the length of the part, long hold on the button to stop. And now I've recorded that scan in one pass. Okay. Now, you notice a couple more views have filled in. Here on the left, these are overview C scans. So a map, if you will, looking down on top of the part. You can select different data to look at here. In this case, this upper overview is looking at amplitude in gate A. So whatever the amplitude of the signal is in the green gate is being shown on this view. And on the view down here, we're looking at the time of flight in gate B. So we have gate B tracking our back wall, looking for defects or corrosion or whatever coming in from the back of the part. And the upper view here is amplitude in gate A. Now you notice the A scan and E scan are frozen at this point. I have a crosshair that's available on the overview, and you notice the crosshair is synchronized between the views. So if wherever I put the crosshair, that is going to show me a sector or an E scan along the vertical crosshair. So this E scan is looking right across that vertical crosshair. And the A scan to go with it is coming from directly under the intersection. So if I move the crosshair down to this indication, I see that that hole that's coming up from the back is at about 10 millimeters depth. If I look at this hole, I see it's more like 7.5 or 8 millimeters. Actually, gate A is telling me it's 6.5 millimeters. Okay. Now, the overview gives me a map of all of the area that I scanned, looking down from the top like so. Now, if I just wanted to zoom in on a certain area, like just this little bit, I can draw a selection box on the overview. And the active C-scan right here is giving me a zoomed in view of just what's underneath there. And down here in the lower right is my B scan, which is a view looking in from the side this way. So whatever's selected between the bounds of the box, I'm looking in from the side. And if I select just that center row of holes, we see 3 holes of different sizes, all close to the same depth, right? They're all at about the same depth. If I change my selection box to look this way, now I've got these 2 holes are at different depths, but because I'm looking in from the side, I see both holes. Both holes are within the selection box. I'm looking back through a view that direction. So if I double click in any one of these views, I can blow that view up to full screen. So if I need a little bit more resolution to zoom in on something, I can always blow it up to full screen and go back down. Okay. And there I accidentally moved my box, but now the active C-scan and the B-scan also give us some measurement tools. So if I come into the active and I draw a box, I can begin to get some measurements around width and length of that hole. And maybe I want to zoom in on that just a little more carefully. There we go. Pop back up to full screen. So now it's a little bit easier to put the edges of my selection box at sort of the 3 dB down points on that hole. And I can begin to get an idea of the size, the diameter of that hole. Okay. And I get some additional information about that. I get the minimum thickness, maximum thickness seen within the selection box, some amplitude information, other useful measurements about this. And always at the upper right corner, I can see my current position of the crosshair with respect to the overall scan. Okay. Now, when we record a scan like this, all of the RF data, all of the A-scan data for every single shot is stored with the scans. So if I were to save this as a data file, I can come back later, just load the data file, and if I want to evaluate it in a different way by, say, changing my gate position, you notice I can change the gate position, and now I'm not going to see some of those deeper holes on my amplitude and gate A view because the hole is now outside the gate. I can move my gate back and get that information back. Okay. So lots of tools here to work with. Generally, when you draw a measurement box on either the B scan or the overview C scan, the active, I'm sorry, draw a measurement box on the active C scan, the crosshairs will snap to the highest amplitude seen within any of the shots in that box. So that can become a helpful tool as well. And again, you can always change your beam selector up here to see the A scan that is directly underneath the beam cursor on your E scan. Okay. With that, I'll throw it back to Benny to take a look at a composite part and building a TCG.
Thank you, Dan. So I prepared a step block of composite here. And with this system, we also have integrated in this electronics the time bracket gain function. I pre-configured the setup like this that the positions I want to calibrate on are already mentioned in the software. You will have a checklist here and can go to different points. You can pre-select, which makes it easier later on to calibrate. In the first place, we are calibrating now the 3.8 millimeter, and I will just pre-wet the system and hit the caliper down here. What it then says me, it's now active recording the TCG, and as soon as I'm ready and have this the RotoArray set to the corresponding step of the block, I can hit the caliper again. Make sure that the signal down here is kind of straight. This test plate here has also some indications in there, so you don't want to calibrate on any flaw, any delamination that's in this test piece. Therefore, make sure you have a kind of straight backwall line here. Down there, just for your information, this is the view of all beams where you can see the amplitude which is within the gate. When I now hit the calibrate button, it will move the amplitude of this signal at the step block to 80%, which is also pre-configured in the software, and will tell me that this point was successfully calibrated. I will move to the next point, and again there, looking for straight line, almost straight line. I will hit again the caliper. It will pull it up to 80% and directs me to the next point. So you see there is an automatic gate movement which directly places it to the corresponding step height you have there. And there you also search for an area which is kind of stable. Hit the caliper again, and it will increase the gain. And the last step here in this case, which is already at roughly 19.5 millimeter, you search for an area which is not hidden by any flaw. There you go, and then hit the caliper again, and it will try to move it up. And for sure, it did not work. Okay, you can start over. So if it's not working, it will throw you back, and then just search for another area. Maybe the wetting was not proper. There you go. And hit again. Maybe we start again. Sorry for that. Okay. So again, the first step, calibrate. Then we go to the next. Also there, calibrate. Then to the third one. And now again, the last one. Okay. So that's a better signal. Should not happen like this. Start over again. Okay, just walking through the steps again. I must say we are just applying 15 volt here, so it might already be too low for this thickness we have there, because you see a lot of noise is coming in. That's what's applied there as well. Okay. It will not do it right now. It did in the demo. That's the target amplitude. I can increase the range I accept for that. Having a hard time. So now again. With a better test piece, it would work better. Okay, barely, it passed. And what we can do now is we go to the scan mode to check if we've seen anything. We just use the green gate, the gate A here, to capture everything. I will go back to the start button, make it slow again. The orange curve just shows you which TCG gain is applied to the certain points. This is the points you just calibrated. And I will do a scan of this plate now. Just hit record, and then we'll go through it. And there you go. With adjusting the calibrate a little bit, you will see more. It captured those drilled holes here. We have some delaminations on this test plate. You might, now it's too dark on this camera in here, and the different thicknesses are recorded down here. And that's it for the TCG calibration. But as we've seen, it's always crucial to have a test piece that has a proper signal and to stay in a range where the system is working properly. So maybe the variation was too big for that. With that, I will pass it back to Dan.
All right, thank you, Benny. I have here another set of samples to look at. This time we have some carbon fiber composite. This part is a very nice part to test with this material, with this RotoArray. The RotoArray is just a little bit wider than the part, which makes for a nice fit. We have two parts here, one that's believed by the manufacturer to be a good part. Has a couple of small inclusions in it, some small bubbles. Have another part here that has some more gross delaminations in the middle. So we'll take a look at both of those. Each one of these parts has a slight taper on the end right at the beginning of the scan. But with that, everything's set up. Let's frisk this a little bit. Give it a little bit of back and forth to make sure we're coupled. And our start button. Do a scan. And could have used just a little bit more water. It didn't couple up perfectly on the first try. But you notice we built a little bit of a jig here. End that scan. We built a little bit of a jig to help with scanning in this case. Because the tire is wider than the part being tested, we just have a couple of rails on either side of the part to get everything up to about the same height. And I put a little stop on the back just to help with alignment. But here we can see this part is relatively clear. Looking at our overview C-scan, I can see a couple of little bright indications here. So let's zoom in and take a look at those. Find our, there we go, get our crosshair on the screen where we can see what we're doing. And now we see we have a little bubble that's right about 2.5 millimeters deep. It's very close to the surface. If we take a look at different areas here on the overview C-scan, look at some of these different indications. There's a small indication more in the middle of the part. Let's look down here. Again, very close to the surface. We have a bright one over here in the corner. Again, very close to the surface. So there's some consistency to where these bubbles appeared during the layup. One or two of them are down in the middle, but mostly they're small indications and they're more or less in the top layer or the top 2 layers possibly of the layup. Okay. So now if I swap that part out, I have another one here. Same basic part, by design at least, but a different part. Let's get some water on here to couple up. And we'll clear that. And start a fresh scan. And here's what we see on this part. So let's stop the scan. We'll zoom into this area. And what we can see here, both in the B scan and in the E scan, is that we've got lots of indications at different depths in the part. We can see that they're larger in area, right? We have large areas with issues, and we have larger continuous areas. These aren't just little bubbles. These are major delaminations in the layup, and they're down in the middle. Okay? Because we're looking at gate A on the top and gate B on the bottom, we can see where some of these delaminations are shadowing the back wall. So where we have very light areas on the gate B C-scan down here at the bottom, these are areas that are being shadowed by the delaminations in the middle of the material. Get out into some clear material here. We can see our back wall showing up more prominently. But when we look at areas where some of these large delaminations are, we see our back wall drops out considerably, being shadowed by the middle layer indications. So again, a part that's very well suited to inspection with the RotoArray. Composites in general, this one is roughly 10 millimeters thick, some taper to it. But again, we can see both small bubbles in near the surface, deep in, And of course, the gross delaminations show up very well with this technique. So Benny, I'll hand it back to you, and we'll go on to the next part.
Yes. So what I prepared here is a small test piece of a fuselage. You see, I already lined up this test piece here with overlapping scans. And what we can see here is an index scanning, a manual index scanning. With those buttons, you can start the recording and have a guide laser. And I will go through this first line here, recording. At the end, I will hit pause. So I make sure there's no signals recorded anymore. I will go to the next line, align the probe. And as soon as I think I'm good, I will hit the index button. So the software jumps to the next line and hit the record button again. And then we'll go through the second line. And the same at the end, I hit the pause button, go to the next line. Hit the index button, start again, and then do the next scan. We already see a defect here, which is, maybe you can see it on the screen as well. Marked on this test plate, there's a crack inside on the surface. And do the next line. And to finish it up, doing the last line. Again, index and continue. And I will go to the next line. With a long press, I will stop the recording and we can have a look at the scan here. Like I said, you have stringers here, supports of this fuselage. And in this area, you will see the flaw of the signal. Yeah, we got basically a backwall loss there. And when you look at the plate, I think you cannot see it there, but here's really a crack inside those layers, and that's what's indicated here. What I just wanted basically to show that there's also a capability of index scanning, and you have two ways to do it. You have a unidirectional scan, which always starts from one position, but you can also do a bidirectional scan. So you can scan the first line forward, index, go to the next line, and go backward again. Also, this is recorded here, and which allows for much faster scanning. With this quick scan, I hand it back to you, Dan.
All right. Well, the final part that I'd like to share with you today is a welded steel plate. There's a weld line that runs diagonally across the plate, sort of on this line, as you can see. And the weld line was ground off. The goal for the folks that put this together was to just grind the weld flush with the plate on either side. And they were curious about how effectively they were making that grind. Did they grind in a way that would scallop out the part? So is the weld line being ground too thin, was the question. So if we try to do this test with a rigid array, like our DM array, as we run it along the part, if there's a place that's scalloped out or a thin area from the top side, the probe will bridge across that, and you'll end up with a gap between the plate and the bottom of the probe, right where it's scalloped out. So what will happen then is you get a bubble of water underneath there, a bubble of couplant, and water being about 1/4 the acoustic velocity of steel, that thin layer of water between the probe and the steel will actually appear as 4 times its thickness in steel. So if you had 10 thousandths of water between the face of the probe and the part, that would look like an additional 40 thousandths of an inch of steel. So this was a little bit of a challenging application with the DM array. However, the nice thing with the RotoArray is with this flexible tire, that conforms to the shape of the grind, and then using interface start mode, we get the true thickness of the steel as opposed to the thickness impacted by that layer of water. So let's do a scan here. There we go. And stop. And we can see our weld line stand out rather nicely. The grind on either side of the weld, it's a little more subtle in the change of colors there, but you can see all of those things going on. And you can see down in this area, we've got some indications where things are looking much thinner as well. So let's take our crosshairs, get down here and take a look just somewhere along the weld line. And if we look at our E-scan, and again, that's going to be, in this case, looking across the weld this way, we can see some contours to the steel from the grinding. And let's see here if we go. We're actually looking at the first and second back walls here. Gate A is looking at the first back wall echo. Gate B is looking at the second back wall echo. So gate B is going to be a little bit more sensitive to what's going on in terms of total thickness of the material. But let's take a look at what's happening over here in this area. That appears to be more of a dropout. Most likely I wasn't coupled very well right there. Okay. So again, the line of the weld shows up very nicely here, and the grind area. And we can come in and take measurements around thickness in particular areas. Again, it shows up very nicely in the sector scan, in the B scan, looking in from the edge. But the fact that we have the conformal tire and the interface start mode in this application makes a big difference in being able to deal with thickness variation, where the variation can come on both the top and bottom surface of the part. Okay, so that's it for the steel weld application. Benny, back to you to wrap up.
Thanks, Dan. Maybe for this last part, I have a corrosion test plate here. I will scan as well. So basically, the first design for that was for composite testing, so for the aerospace industry, but still we are looking for more applications. And one of them is the corrosion, like you already said, with a weld scan. Steel is still application we can target as well. I will do also an index scan and will show you afterwards the backside of this testing piece. I hit record and also do the first line here. I have my laser guides as well. First line. We see there's on the right hand side, there's a step, steel step, which is recorded. Then we go over to the next area where we see the center of this test plate, which has some area of corrosion, which has some flat bottom holes as well in there, to see the minimum wall thickness. I run again here. And the last line. To complete the picture of this test plate. And what you can see here is really those these holes that are made here. I will just turn it around. Maybe you can kind of see it in the screen. We see this area here with those two holes in there. We see those 3 holes here up there. Yeah, basically all the errors we see on the test plate also appears on the picture. And that's just a basic application in addition to what Dan showed. This is capable also for doing the steel testing and corrosion testing. And with this practical session finishing now, I will pass it back to you, Vincent, to wrap up and start the Q&A.
Thank you, Benny, and Dan for the demonstrations. Yeah, we have quite a lot of questions. Let's start on the top. Let me just check. Give me a. There you go. What is the maximum? What is the minimum maximum effect of thickness in composites?
Well, that's basically depending on the material itself and the dampening itself. Because of the frequency, I would say typically it's 7 to 10 millimeter we would test here. Technically, we have a water delay of roughly of 21 millimeter. So 35 to 40 millimeter might be the maximum to be tested, depending on the energy and what you want to see there. We now tested with mostly with an aperture of 4 elements. If you just want to do wall thickness measurements, you can increase the aperture, which gives you more energy to detect the back wall.
Okay, thank you. What is the roughness on the surface, and can the test be done with coating?
Because we have a water coupling, we can also test on some more rough material, but this is then for sure influencing the signal transmission. Depending on what coating, it might be possible, but for that, it would be better to reach out with a test piece or something, some more detail on that, and we can figure it out in our application lab, what we can do there.
Okay, thank you. Can you create the workflow it meant to create?
Basically, you can. If it's required to have a modified workflow, also I would recommend to contact our application lab, which then can help you to do an application which is tailored to your workflow. Maybe not everyone needs to do that element check up front. Also, maybe some procedures can be in there, but if you have questions like this and you have some application in mind where you want to have a workflow tailored to your application, just contact as well our application lab for that.
Good, thank you. Thank you for that. What is the maximum distance you can acquire?
For the electronics itself, it is theoretically 480 millimeters, but we know that the energy would not be enough in these depths. So that's just a theoretical value. The tire itself, like I said, has a delay line of 21 millimeter, which translates for steel, for example, to max, I would say 80 millimeters before the second signal of the interface echo is in the way. Yeah.
Okay. What is the near surface resolution?
Also, they are depending on the material. We would say from 2 to 3 millimeter, we can start with this RotoArray.
2 to 3 millimeter. Okay. We can skip that one. Yeah, that's a. Thank you very much. What is the maximum area you can configure? It's
okay.
Probably tire broad, right? How broad?
I mean, basically, I think it's aiming at the size of the scan we can do. And in total, the limitation by the software is 10 by 10 meters.
Can you inspect the curved parts, and what is the minimum radius?
Yes, we can. The minimum radius is a little bit determined on also the thickness of the part. So which area gives you the reflection. As well, there I would recommend to contact our application lab to see what we can do with the application you have in mind. And yeah, there's also ways to kind of adapt to your test piece. Our application lab is really happy to help there.
Okay. I think there are no more questions. This platform doesn't allow to be unmuted, so if there are any more questions, please don't hesitate to put them in the comment box. We're more than willing to answer all the questions. I think what we've tried to show is the versatility of the system, and the RotoArray comPAct, and especially the comPAct technology, has been designed in the beginning for the aerospace market, but we're quickly finding out that it's also fantastic technology with regards to corrosion, some parts of weld, and it quickly runs into a very versatile system. If there are no more questions, we will be going towards the closure. Louise, Solar, I'd like to thank you, and Derek, thank you very much for your questions. It's great to also always have some interactive discussions during the sessions. Please see this as a start of the technology. The comPAct technology, the RotoArray is the first that you've seen from us. We are looking at how can we diversify into other elements, markets as well. One of our current ideas is to really step into the 3.5 megahertz frequency, to go a bit lower. But we also would like to have your feedback, right? Please don't hesitate to reach out to us, whether it's me, whether it's Benny, or your channel partner, or your local sales manager, as well as the sales directors that you can see on the screen, to come up with your questions, because we see that this technology can be way more versatile than it currently is, and this is just the first step. So if you have any application or industry specific items that you would like to address, or where you see a market that it can be useful for, as Benny already said, reach out to us, and specialists like Dan and Ben are there to support us together with the application lab to really dig into this kind of technology. You can always reach us through LinkedIn. Also, our email addresses from Baker Hughes are listed here, so please reach out to us. We also have our global website named here below. So if you click on the link, it will take you to the website of the RotoArray comPAct. Let me do a final check. Are there any new questions? I don't see anything else. No, not at this moment in time. Then I would like to thank everybody, the team of Waygate, and especially all our customers, channel partners, and partners that were on. I'd like to thank you for your time, and we hope to hear from you soon.